Hello everyone, my name is Edison Hong, and this is my fourth lab, Oscillations for Physics. So, the purpose of the lab is to look into the motion of the spring mass system with mass oscillating in an arc. And the software we're going to be using today is the tracker software to track the observed position and the glow script to compute and predict the motion of the graph and energy changes. And our goals would be to determine if the model follows the energy principle, and our result at the end is the system's total energy remains constant at zero and demonstrates the energy principle. So, what exactly are the principles of the lab? So, we have Newton's second law first, which is the system change in momentum proportional to the net force applied. So, this is our spring mass system, as you can see in the graph there. We have the force of the spring acting upwards and the gravity acting downwards, and we could write that as a force of spring plus the force of gravity. And there is an expanded version of the formula. And then for the energy principle, it's the system's change in energy, which is the sum of work done by surroundings and thermal energy exchanged with surroundings. So we're going to have to isolate the system so there's no interactions with the surroundings. So that means the change in energy of the system should be zero. And for the system, we have kinetic, potential, and gravitational energy, which are all equal to zero, as you can see there in the formula. And then those are some other equations that are useful as well. So as you can see here, I use the tracker model to track every key point of the mass, while it's tilting back and forth. And then the initial position I recorded as 0.285, um, and some of the other initial conditions like velocity and molecular mass. So now we have to find the other initial conditions. So I have to define a couple initial conditions first before I do the computational model. And we have to solve for the period first. And the period is how much time it takes to complete one cycle. So if the cycle starts from one end and goes to the other and back, that's one cycle. So I looked at the graph for the motion in the y direction and found three different periods and averaged them, as you can see there, solving for t. So the period is related to k. So I solved for the spring stiffness, and therefore I could find the relaxed length of the spring there, demonstrated by those formulas. So as you can see here, I inputted all the initial conditions, and then I inputted the spring length and the directions and the system energies. And the spring length can be found by subtracting the relaxed length of the spring form from the stretched length. So for the energies, I used the formula kinetic, gravitational, and spring potential energy and added them together to get the initial energy of the system, as you can see there with some of the formulas. So now it's time for the while loop, and the while loop will iterate through each time step and calculate the energy present. So the total time for me was 9.3 seconds, and I calculated the gravitational and spring force and the net force. And if we have the net force at each time quantity, then we can find the velocity and position of our mass. And using these quantities, we can find the kinetic and potential energies of our system and the change in energy at each time step, as you can see by the formulas represented there. So now we're going to be comparing the computational versus observed model. So the two diagrams shown is what graphically represents the oscillating functions. So in the beginning of the time, the two models overlap, but over time they start to deviate more, as you can see from the two graphs there. And one of the possible errors of that deviation could be the system is not isolated from the surroundings in reality, and there's usually work done from the surroundings. And a second possible error could be the inaccurate center on mass placement of the tracker model. So now we'll have other questions that we need to satisfy. And one of them is the energy principle satisfied? And yes, it is, as you can see the graph there. No external forces affect the isolated system, and change in energy must be zero. And even though different types of energy are in the system, the graph shows the total change in energy is always zero. So now I'm going to compare the oscillation cycles and what it exactly means. So using the tracker analysis, I found the period of oscillating in the x and y directions by looking at one oscillation. As you can see there, found it for the x and y directions, 1.71 seconds, 1.54 seconds. And some of the differences there are due to two different simple harmonic motions in different axes. And the second one is, tracker errors. And choosing different directions produces deviations in the period, which affects the spring constant and graphs. And thank you very much for listening today.